Ni hao. Hello. This is the 16th lesson in heat transfer. In this lesson, we will begin our unit on convection heat transfer. This lesson will focus on introducing the field of convection heat transfer and the idea of the boundary layer. There will be 3 parts to this lesson. In the first part, we will talk about what the goal of convection heat transfer analysis is. By the end of this lesson, you should be able to explain what the fundamental question underpinning convection heat transfer is. You should also be able to explain why fluid mechanics is an important part of convection heat transfer. Finally, you should be able to describe why determining a single value for the convection heat transfer coefficient is tough. It is not an easy or straightforward task due to the complexities of the fluid motion and the interaction of the fluid motion on the heat transfer at the solid-fluid interface. On with the first lesson. Convection, and I'll remind you on the next slide here, is really just conduction, right? I told you at the beginning of the class to think about convection as conduction plus advection. And we talked about how when you have fluid flowing over a solid and you have a fluid-solid interface, that at the interface, the fluid is not moving because of the no-slip condition. And so conduction applies there. And so the influence of the flow is really to modify the temperature gradient at the interface to enhance it over what you would see if there was no fluid motion at all. So we capture that influence through this convection coefficient. And when we're thinking about convection heat transfer, really the question that we're asking is, what is the right value for the convection heat transfer coefficient? Like up to this point in class, it's just been handed to us in the problem statements. You know, they say, use this value. And the values that you've seen are typical numbers for the conditions that have gone with it. You've seen higher numbers for convection with liquids than in gases, right? Because liquids are better conductors, and so they lead to better conduction at the interface, and so you have higher heat transfer coefficients. But now we really want to dig in and say, like, how do you come up with a number? How would you come up with a number if it wasn't given to you? And I've shown a picture here taken from the web, so it's got the watermark there to give credit, of 3 different lights. Do you recognize these? Does anybody see these light bulbs anymore in buildings? Do you know what these are even called anymore? They're called incandescent light bulbs. And used to be that the world was full of them. And then we got smarter. Do you recognize this one? Do you know what this one's called?
Fluorescent.
Yeah, that's right. Yeah, it's called a compact fluorescent bulb. So some of the lights in my office here are fluorescent light bulbs, but they're not compact because they're nice and big. These are compact because they fit in the traditional sockets that the incandescent light bulbs used to go in. And then here on the left, this is an LED, which is probably what you're familiar with now, because that's what you see on the shelves, because these are good. Can you see from the picture why the LED, do you have a sense perhaps from the picture of why the LED is better than an incandescent bulb?
It doesn't release as much heat.
Yeah, that's right. What about the picture gave you a sense of that?
There weren't like the swirly things. I don't know if they're like eddies or those things coming off of it.
That's a great description. Swirly, that's what it is. It's swirling hot air. So the incandescent light bulb, when it operates, they get really hot because they're actually terrible lighting devices. Only about 10% of the energy that the bulb draws, the electrical energy that the bulb draws, actually goes into producing light. The rest of it is just shows up as thermal energy inside of the bulb casing. And that thermal energy, of course, has to get out, right? So there's thermal energy generated on the inside. It's got to go somewhere. It can't stay on the inside, right, when the bulb is at steady state. So the bulb heats up in order to drive the energy through its surface. And at the surface, there's convection heat transfer, in particular, a type of convection called natural convection, because the fluid motion is actually driven by the heating process. And so you end up heating up the air at the surface of the bulb, and that hot air flows up and away from the bulb surface. And of course, when the hot air flows up and away, mass has to be conserved. And so some air has to flow in and take its place. And that air flows in from the cooler environment. And that's how you have an enhancement of heat transfer over conduction, right? So the cold air comes in, it takes the place of hot air, it takes some energy up with it as it goes, and then it flows away from the system. But you can tell, like Jay said, that there's a lot more of that happening on the incandescent bulb because this hot plume is much more it's much more stabilized, it's much more visual, it's easier to see because it's a lot stronger. There's a lot higher velocities in that hot plume. You can see the CFL perhaps is a little better, but there's still a significant amount of upward flow of hot air in the CFL bulb. And if you've ever worked with them, they get hot too. So they're better than the incandescent light bulbs. They're a little bit better. I don't remember what the efficiency is, but I think it's more like 50-50. But so you still have a lot of just thermal energy that you have to just dissipate away. And that's energy that, especially say in the summertime here in Indiana, at least when it's really hot and we're running our air conditionings, if we have our light bulbs on, we're paying for the light. We're putting the thermal energy into our houses, and then we have to pay again with the air conditioning to take that energy out. So it's disastrous. In the wintertime, perhaps you could make the argument that, well, at least that's helping to keep the house hot, right? To keep the house warm. But I would say that this is like a one-to-one. It's not the best way to heat your house, okay? The LED, though, we don't see this hot plume. Like there's maybe some side flow out the sides, but we don't see it's hot enough to really drive that airflow up, right? So if we wanted to model, right, how hot does the incandescent light bulb get versus the LED light bulb? And we knew that what the thermal energy generation was. If we wanted to calculate the heat transfer rate at the surface and thus predict the temperature on the inside, we'd have to know what H is here, right? And do you think that there's a single value of H that characterizes the nature of the heat transfer across the surface at the base of this bulb, say down here, versus the top right here? No, right? I mean, the flow is not that simple. It looks more complicated than that. That's exactly right. So that's what we have to try to come up with a way to get a grasp on this. And these types of situations, I'm giving you a light bulb as an example, but they show up all over the place, right? They show up all over the place. Okay, so my goals in this unit are to really emphasize the physics, because the physics is hard, because it requires flow, and fluid motion is tough, right? So we're going to talk a lot about the nature of the flow and what it looks like, and taking information about what it looks like and trying to say something qualitatively about what that means for the convection coefficient. When you actually run problems, you're going to see that problems really come down to finding the right empirical equation for that particular flow situation, and then you just kind of plug and chug. So it's about linking the particular problem type to someone that's done an experiment with a similar problem type and taking advantage of that information. So it's very empirically driven convection heat transfer. So that will go a lot quicker. It's going to not take me very long to teach you how to find the right equation to grab. So that's why I want to emphasize the physics that goes on that gives rise to this type of situation.